Hey everyone! Welcome to this explainer on conditional execution. Today we're unpacking the foundational mechanism that allows software programs to break away from a strict top-to-bottom linear path. If you've ever wondered how a rigid, logic-based machine can navigate the highly variable, unpredictable scenarios of the real world, well, the concepts we're about to cover are the literal blueprint for that capability. So let's just dive right into it. A computer, at its core, relies exclusively on ones and zeros, right? So how on earth does it handle the infinite, super messy, nuanced decisions of the actual world? Think about it. How does an automated car know exactly when to brake? Or how does a streaming service know exactly what movie to recommend you next? It all boils down to translating complex reality into simple, undeniable states. It pulls us off through something called conditional execution. Honestly, it perfectly mimics how we make logical decisions, but it does it by forcing electronic states into strict binary outcomes. It takes a condition like, hey, is the temperature above 70 degrees, and it reduces that to a definitive true or false. Based entirely on that Boolean result, the CPU decides which specific branch of your code to run next, completely ignoring all the other branches. Here is our roadmap for today. We'll start with 1, the binary brain, and 2, Boolean logic and operators. Then we'll cover 3, the if-else hierarchy, and 4, short circuits and logical chaining. Finally, we'll look at writing cleaner logic by 5, escaping nested spaghetti code, and putting 6 guard clauses in action. All right, let's jump into section 1, the binary brain. I absolutely love this quote from one of our sources. The computer is not guessing, it is just checking. You know, programming can sometimes feel a bit like magic, but the reality is actually much simpler. Think about your own day-to-day life. If it's raining outside, you grab an umbrella. If you're hungry, you eat something. You're already running this logic in your head. Programming is literally just writing that logic out step by step. The computer isn't anticipating the future. It's simply checking a predefined condition to see if it resolves to true or false at that exact millisecond. Moving on to section 2, Boolean logic and operators. Now, this is where things get really cool. This is the bridge between abstract math and physical computer hardware. Hardware logic gates act as physical checkpoints for electrical signals inside the machine's processor. Thanks to Boolean algebra, which uses a 1 to represent true and a 0 to represent false, when we write code, these physical logic gates are what actually process our mathematical comparisons. It's a literal intersection between physical electricity and software logic. And to trigger those gates, software programs utilize these exact relational and logical operators. Take relational operators, for example. They compare two variables. They check things like, is variable A strictly equal to variable B? Or is A greater than or equal to B? Then you have logical operators like and, or, and not. These are a game changer because they let us string multiple expressions together. By using these operators, developers can compress multi-layered, highly complex real-world conditions into one single definitive true or false outcome. Okay, section 3, the if-else hierarchy. Think of this structure using the metaphor of walking down a long hallway. The computer approaches the very first door, which is the if block. It checks the condition. Can I enter? If the answer is true, boom, it runs the code inside, and, this is absolutely crucial, it stops and skips the rest of the structure. But if it's false, the door is locked, so it moves to the next door. These are the elif or else if blocks, which evaluate secondary conditions sequentially. Finally, if every single previous door was locked, it reaches the else block at the end of the hall. This is your structural fallback. It ensures that the program always has a valid path to take if none of the specific conditions are met. Because remember, the CPU only gets to choose one path. Next up, section 4, short circuits and logical chaining. So, in the real world, we rarely just ask one question at a time. By chaining operators together using and or, we compound our states. But here is the really clever part. Modern languages like Python and C++ use something called short-circuit evaluation. Imagine an and statement checking two rules. Is the user an admin, and is their password cracked? Well, if the very first check, is the user an admin, returns false, the computer already knows the entire statement can never be true. So it simply stops. It doesn't even bother checking the password. It short circuits. This guarantees a definitive answer while instantly saving processing power and avoiding totally unnecessary calculations. All right, section 5, escaping nested spaghetti code. Okay, we have all seen this. Deeply nested conditionals. An if, inside an if, inside an if, that just continuously push your code's indentation further and further to the right. Experts like refactoring guru notoriously call this the arrow of pain and woe. Or you might just know it as spaghetti code. When you nest too deeply, you force the next programmer who reads our code to keep a massive mental checklist of exactly which conditions are true or false at any given indented level. It becomes a massive source of logical bugs. To solve this, professionals use a pro-level architecture to flatten things out. Instead of chaotic, deeply nested logic blocks, we can flatten our code using guard clauses. Instead of nesting the true path inside some massive if block, a guard clause checks the invalid conditions right up front and immediately returns out of the function if a condition fails. It essentially guards the rest of your code. If you make it past those initial checks, you know for sure you're in a guaranteed safe state, and your code remains perfectly flat and incredibly easy to read. Bringing us to Section 6, Guard Clauses in Action. Let's actually walk through building an automated access control gate together. Step 1, we drop in our guard clause. If the user is unauthorized, we refuse access immediately and exit. The remaining code doesn't even run. Step 2, okay, they passed the guard. Now we use compounded logic to evaluate a secondary state. Elif, the user's authorized, and the system is under maintenance, we allow restricted bypass access. Finally, step 3 is our structural fallback. Else, meaning they are authorized and there is no maintenance, we safely grant full access. This is exactly how professional systems manage complex rules securely and efficiently. Before we wrap up, I want to leave you with a final, somewhat provocative thought. At the end of the day, even the most advanced, complex software flows boil down to physical gates channeling electricity into true or false states. So if literally everything in the digital world, from a simple Python script opening a gate to a massive artificial intelligence brain driving a car, is built entirely on these binary conditionals, what actually separates programmed conditions from genuine intelligence? Are we just running an unimaginably massive set of if-else statements in our own heads? Definitely something to think about. Thank you so much for joining me for this explainer, and I'll catch you next time.